In this video, we'll be dealing with the following scenario. The capacitor is charged to 50 volts. The switch closes at t equals 0 seconds. Draw a graph showing the magnetic field strength as a function of time at the position of the dot. On your graph, indicate the maximum field strength and provide an appropriate numerical scale on the horizontal axis. So the problem states that the capacitor on this circuit starts out fully charged, and once the switch closes, the capacitor will discharge. And so we'll start out with the equation Q as a function of time equals Q naught times e to the negative t over RC, which is the equation for a discharging capacitor. Now, just a plain old charge gives rise to electric fields, but we're interested in a magnetic field, and current or a moving charge gives rise to a magnetic field. And so we'll use the relationship current is equal to the change in charge over change in time. And since current and charge are directly proportional, we'll just replace charge in this equation with current. And that'll give us the equation I equals I max times e to the negative t over RC. And we'll use the relationship in Ohm's law to get I max, or current in general, equals V over R, or voltage over resistance. And that'll give us the equation V over R times e to the negative t over RC. And now, plugging in the values that are given in the problem statement, we'll get 50 volts over 5 ohms times e to the negative t over 1 times 10 to the negative 5 seconds. And I got 1 times 10 to the negative 5 seconds by solving RC, or resistance times capacitance, which is 5 ohms times 2 times 10 to the negative 6 farads, which is just the conversion from the 2 microfarads given in the problem to farads, and that yields 1 times 10 to the negative 5th seconds. And simplification will give us 10 amps times e to the negative t over 1 times 10 to the negative 5 seconds. And for magnetic field, or the magnetic field at this point, we'll be using the equation for a magnetic field of a line, because this line of the circuit will be giving off a magnetic field that will affect this point 1 centimeter away from the circuit. And so the equation for the magnetic field of a line is mu naught times I over 2 pi d. And so we'll plug in what we found for current earlier, and we'll get mu naught over 2 pi d times 10 amps times e to the negative t over 1 times 10 to the negative 5 seconds. And so plugging in our known values, mu naught is 4 pi times 10 to the negative 7, and that's over 2 pi, and the distance between the line and the dot where we're observing the magnetic field strength is 1 times 10 to the negative 2 meters, which is the 1 centimeter converted to meters, times what we found for current earlier. And that'll yield our general equation for the graph that we'll be producing later, and that's 2 times 10 to the negative 4 Tesla times e to the negative t over 1 times 10 to the negative 5 seconds. And to find the magnetic field at t equals 0, we plug in 0 for t, and that'll give us e to the 0, which is 1, and that'll give us 2 times 10 to the negative 4 Tesla. And here is the graph that I was able to produce from the general equation above. And to get the other plots of the graph, you just plug in other times in t in the equation. And so here is the maximum magnetic field strength given off, which is 2 times 10 to the negative 4 Tesla, which is at time t equals 0. And the magnetic field will decrease as time goes on.